another enlightening session of Jigyasa series of talks being organized jointly by RIC and All India Services Pensioner Association of Rajasthan. The goal of this series is to disseminate knowledge and promote lifelong learning. The theme for today's talk is the enigmatic black holes, where to find them. It is a subject that takes us deep into the mysteries of our universe, a journey through the most fascinating and puzzling phenomena known to science. We welcome on stage Shri Umesh Mohan Sahai ji, current President of All India Services Pensioner Association of Rajasthan and a distinguished member of the 1977 batch of the Indian Forest Services. May I request everyone to join me in a warm round of applause to welcome Shri Sahai ji. He may kindly come on the stage to preside over the function. Everybody please put your hands together for him. Today, we are truly privileged to host an eminent astrophysicist and academic leader, Dr. Somak Roychoudhary, Vice Chancellor of Ashoka University. Dr. Somak Roychoudhary's pioneer research in cosmology and astrophysics has illuminated our understanding of the cosmos and inspired countless curious minds. I request him to kindly come on the stage. Let's all extend a huge round of applause to welcome Dr. Somak Roychoudhary on stage. I now call upon Director RIC Shri N.C. Goyal to come on stage to felicitate our distinguished speaker, Professor Roychoudhary. Everybody please put your hands together. Without further ado, may I now request Shri Sahai to formally introduce Professor Somak Roychoudhary to the audience and also request the audience to please keep your mobile phones on silent modes. Thank you. Yeah.
It's my privilege to introduce a distinguished speaker to you today, Dr. Somak Roychoudhary. As informed to you, Dr. Roychoudhary currently serves as a Vice Chancellor of Ashoka University, where he is also a Professor of Physics. Before taking on to this role, he led the Inter-University Center for Astronomy and Astrophysics at IUCCA, Pune, as its director, which is a testament to his standing in the scientific community. His academic journey is exceptional, starting with a degree from Presidency College, University of Calcutta, and continuing with studies in physics at Trinity College, University of Oxford. Supported by an Shiv Dasani scholarship, he earned his PhD in astrophysics from University of Cambridge, where his excellence was recognized with J.T. Knight Prize. Dr. Roychoudhary's career includes significant international experience, notably as a Smithsonian Fellow at the Harvard Smithsonian Center for Astrophysics, CFA. While there, he was a part of the crucial NASA project team which built the Chandra X-ray Observatory. He is a man who has not just studied the stars, but has also helped our eyes in the space to see them. Please, and that's what he is here today. Please join me in extending a very warm welcome to Dr. Somak Roychoudhary. And now I request Dr. Choudhary to enlighten us on the enigmatic black holes, where to find them. Thank you.
Thank you very much. I'll actually use this mic, okay? Is this okay? Can you hear me at the back? And thank you very much. This is a privilege for me to come to Jaipur to address you. My first visit to Jaipur was as a second-year undergraduate student from Residency College, where we were brought as a group to see the physics labs at the University of Rajasthan, at that time Babulal Saraf's lab, and to meet the great man. And I still remember how much that lab had an impact on me, and meeting the department at the University of Rajasthan. So you've had a wonderful tradition of physics teaching and research in Jaipur. And I've come back many times since then, notably when I was director of IUCA, where we had to also look at astronomy and space education all over India in various universities and the universities in this area. Anyway, so today I'm going to talk about black holes, which might seem to be quite an exotic thing. People think of black holes as scary things that you encounter in horror movies or science fiction. And a significant amount of interesting work has happened in this area in the last few decades. I've been involved in quite a lot of it. And I just thought I'd demystify them a little and also talk about how it connects to the aspirations of Indian science. And so India is very much involved in a lot of the things that is going on in this space. Can I request you to come and sit here so that you can see the screen? Otherwise you won't be able to. A lot of black holes are touted to the general public as elements of horror. You see these Disney movies which actually talk about infinite space, infinite terror. No force from this world can stop it, as if the black holes are coming to get you. And as I hope that you will leave this hall today knowing that black holes are actually quite nice little things that are not there to get you at all. In fact, as long as you don't go very near them, and it's very, very difficult to get near them because they're very far away, they are not harmful for anybody. In fact, they're very, very interesting, fascinating, and fascination and how awesome they are has essentially inspired so much interest in science in general and science fiction that a lot of this can be overridden now by young people who come into the subject and try to study them. In fact, at Ashoka, I teach a first-year course which is open to everybody, including students of humanities and social sciences, and I talk about space and time and black holes, and I find hundreds of people in my class who are very, very interested in various aspects of it. So it just essentially brings out the imagination in people. So let me first talk about what black holes are. And I understand there are physicists in the audience, there are people who've studied physics, and I hope I'll have some things for you as well in this talk. But I will assume that you don't know much physics. So let me start from the beginning. And let me start from basic school physics and going back to Newton. And the way Newton formulated our idea of what is known as gravity or gravitation. And this is something that we all have encountered in school. There are young people here, and people who are much older than the young people would remember that in school they were all subjected to Newton's laws and Newton's discoveries and the apple that fell on Newton's head. And the idea is that Newton formulated everything as the fact that any two things in the universe are attracting each other by an invisible force, a force that is like a string is connected between them, and they're attracting each other. And this force is called the force of gravity. It's a very long-range force. Things that are very far away from each other in the universe can attract each other, like the sun and the moon, and the sun and the earth and the moon, and the earth and Jupiter, whatever. Everybody is attracting each other in this solar system. And frankly, you and I are also attracting each other for this force. But the gravitational force between us is weak. But they are related to how much mass we have. Yeah. And I'm embarrassed to say my mass is rapidly increasing. And so that increases the gravity. And also, It's inversely proportional, which means into the distance between the two things. So the farther away people go away from each other, these two things go away from each other, the force decreases and decreases the square, right? So this is what Newton introduced as a result of that fantastic ideas that he had in the 1.5 years that he was actually stuck at his aunt's house because the university had shut down because of a pandemic. That kind of pandemic we experienced a few years ago. In Newton's case, his university had shut down, and that's when all these ideas came to him. So this is stuck, and we still study Newton's ideas about gravity in school. And one of the things that came out of Newton's ideas was that in order for us to escape from the Earth, which is actually pulling us due to gravity, we need a certain minimum energy or velocity. Otherwise, we cannot escape from the Earth. As a kid, I used to be quite afraid that if I jump too hard, I might actually fly away. And you will see that that's very difficult to do. You need a minimum velocity, and that velocity is quite high, to jump in order to escape. And that, for those who are mathematically minded, has a formula which is pretty simple, and it's given by this formula which says escape velocity is equal to or proportional to a square root of the mass, which is the mass of the Earth, and also the square root of the radius. So these are two things that connect how much gravity you will have on the Earth. On the moon, the mass is small, the radius is small. It turns out the gravity is very less, very, very little compared to what we have on the Earth. And so you can jump on the moon, you don't feel that much gravity. The escape velocity is very important. That's a Newtonian idea. So now you can try and understand the concept of black holes from this as well, even though it is not strictly correct, and I'll tell you why. But from this classical idea of gravity that Newton gave, you can say that if that is your escape velocity, and we know that the highest velocity that anything can have in nature is the speed of light. So something that has an escape velocity that is larger or equal to the speed of light, then nothing can escape from it, right? And so that is a black hole. A black hole is something from which nothing can escape. So it means this escape velocity is such that it is larger than the speed of light. Make sense? So the question is, how can anything be constructed such that the escape velocity is as high as the speed of light? I'll give you some examples. For the Earth, the escape velocity is 43,000 kilometers per hour. You won't be able to drive your car that fast. Police will catch you. But you can now see my fears as a kid of jumping fast enough so that I can escape from the Earth was unfounded. That's a very high speed. Now, but it's nowhere near the speed of light. The speed of light is 3 lakh kilometers per second, right? So 11 kilometers per second from the Earth is small. If you want to escape from the sun, you can see that that's 600 kilometers per second, right? So the Earth is going around nowhere near that speed, and so the Earth is not going to escape from the sun. But can we make an escape velocity that is very high, such that it exceeds the speed of light? In order to do that, what can you do? So here you are. What you can do, I gave you that formula. The formula says that the escape velocity increases with the mass increasing, or increases with the radius decreasing. So let's see, if you keep the same size and you increase the matter, the mass of something, make it heavier, the escape velocity increases. So we can try doing that. And you can see these are mass increasing, and as the mass increases, the escape velocity increases. So something that you throw up is going to come down. It's not going to escape. It's very hard to increase the mass of something that is fixed. How do you do that? I think it's much easier to do the following. The other way to do this is you decrease the radius, the size, and it becomes denser and denser, and the escape velocity increases. So you can do that. And as you can see, a smaller thing which has the same mass, keep the mass the same. So if you have the Earth and something that is smaller than the Earth, with the same mass, will have a larger escape velocity. So if you now want to make that go up to the speed of light, you just have to scrunch something to a very, very small size. Now this actually came into the heads of a lot of clever people even after Newton talked about gravity. This is not a new concept. John Mitchell, 1783, 100 years after Newton's book on physics, on mechanics, wrote the same thing. He says, look, what happens if we take something like the sun and make it smaller and smaller and smaller so that its escape velocity is much bigger than the speed of light? Then what will happen? You will find what is known as a dark star. No light can come out of it. Laplace in France, who's there in everything, Laplace I think thought of almost everything. Laplace, same thing, independently. So people were already thinking about it, but it was strictly very difficult to work it out mathematically, because as soon as you get closer to the speed of light, a lot of Newton's physics breaks down. So you needed to invent a new kind of physics which would cope with speeds that are very high. Newton's laws actually don't apply. So then, just to remind you, then comes the general theory of relativity at the beginning of the 20th century, about 100 years ago. Newton, I already reminded you, talked about gravity as some kind of a force between two things. Came Einstein, who had the general theory of relativity, who actually formulated a new theory of gravity, which is not taught in school, so many of you will not be familiar with it, which essentially has the same effect for things that are not moving very fast, like you and me. But it also works for things that are moving very, very fast, closer to the speed of light, including light itself. In doing so, Newton did something completely radical. He said actually that whole idea that Newton had, that gravity is actually a force which is like an invisible string connecting two things, is not right. Because when he was very young, he used to think about these things. I mean, there is an essay written by a 15-year-old Einstein, which he gave as a present to his birthday present to his uncle. I don't know how many of you actually gave birthday presents, essays of physics to your uncles. But Einstein was something like that. And he's writing like, what happens if two things are moving very close to the speed of light? Are they attracting each other with gravity? How do they know where they are? This thing is pulling this thing, but by the time this has got to know that this is pulling, but this is also moved. So to explain gravity as this kind of a force is very difficult. So Einstein said, actually, gravity is a very local effect. It's not a force like that. And this is not what we are taught in school, so it might come as a surprise to many of you, that right now we think of gravity as not a force. Einstein said the following. Einstein said, actually, gravity means if I have mass, space around me is distorted. It's curved. And whatever is around me feels the effect of that curve. So for example, the Earth is going around the sun, and that is because the sun has curved the Earth, the space around it, space itself. You don't see it, but space itself is curved. And this Earth is trapped in that curved space. And that is why it is moving around the sun, not because there's an invisible string pulling it. You understand? You can see that with the Earth, there's also a little curvature there. And that's why the moon, which is going around the Earth, is trapped there. If you believe this is true, it solves a lot of the problems with Newton's theory, and it also gives us an idea of quantifying black holes. So for those who are mathematically minded, that's the general theory of relativity. It essentially says if you have a lot of mass, you distort space-time. So this famous equation, on one side is the geometry of space-time, and the other side is the amount of energy or mass something has. He connected the two. That itself, actually, this is a very compact equation. If you write the whole thing out, it takes 3 or 4 pages. But this is the basis of our understanding of gravitation now. And let me tell you, some of the best relativists who have worked on Einstein's theory, contributing to the knowledge of how this works, have come from India. Indians have absolutely led that study of general relativity, so much so that the names you hear nowadays of Hawking and Penrose, etc., their work is based on a lot of Indians who did this work. So Einstein gave us our theory of relativity in 1915, which described gravity. Now, very interestingly, a lot of people would realize that 1915 is in the middle of the First World War. He wrote this paper in German, in a German journal. Who was reading it in 1915? The English-speaking world, America, England, they were fighting Germans. They were not getting these things out of Germany. Actually, they came to India. German people would carry these books to India. The first English translation of Einstein's general theory of relativity was done in Calcutta by two young faculty members called Meghnad Sahai and Satyen Bose. They knew German. They translated it into English. Right? That book is published by Calcutta University. So Einstein's theory became more widely known as the First War ended. But before that, the German professors themselves had a go at figuring out the consequences of this new theory. And the first person to do it was Karl Schwarzschild, who was a professor of mathematics in Göttingen. And he solved Einstein's equations for a spherical object like the Earth or the Sun. He was doing this in his little diary that he carried with him while he fought for Germany in the Russian front in the First War. And while he was doing this, he died. But he had sent his solution on a postcard to Einstein before he died. That Einstein published. A lot of things from that early solution is very well known as a Schwarzschild solution. And our knowledge of how you can make things into black holes is based on that solution that Schwarzschild managed to do, while in the next few months after Einstein's theory was published. So the idea is you can take a star and you scrunch it, make it smaller and smaller and smaller, such that its escape velocity is going to become the speed of light or more. How do you do it? The person who did it was Subramaniam Chandrasekhar. Chandrasekhar, as a young student traveling to Cambridge to do his PhD with Paul Dirac, on the ship had this idea of how to do it. He knew that he had to apply some quantum mechanics to this problem. And he essentially, while he was a student, had worked it out. And thus, from Chandrasekhar's work comes the idea of how to form black holes. The basic idea was done in his work. It's a wonderful story to read, but I'm not going to talk about that. So now, how big do you have to make a star to make it into a black hole such that nothing can escape from it? We call that, on the basis of Schwarzschild's solution of Einstein's equation, the Schwarzschild radius. Remember Karl Schwarzschild, who never got to see his paper published and became so famous? And it's a very simple formula. It says it is twice the gravitational constant times the mass of the star divided by the speed of light squared. Very simple. And that means that if you took the Earth and you scrunch it to something that is about a centimeter across, it becomes a black hole. Can you do it? You read it in the paper, CERN turns out it's LHC, and tomorrow the Earth will turn into a black hole. Not happen. I can turn you into a black hole if I can scrunch you to a fraction of a millimeter. How will I do it? I don't know. Right? You can see that because it's just proportional to mass. So you can figure out what the Earth's mass is, what your mass is, scale it from 1 centimeter, and you can find out what your Schwarzschild radius is. Right? Anybody can turn into a black hole. This is what Einstein gave us. Anything can turn into a black hole. It's easier for stars to become black holes, which is what Chandrasekhar showed. The sun can turn into a black hole if we can actually find a way of getting it to 3 kilometers in radius. That's not going to happen. and the sun will not turn into a black hole. But bigger stars will. Sorry, I don't know why. Oh, sorry, I'm going the wrong direction. Yeah, before that, I just wanted to, I said I'm going to talk about, there are some myths about black holes that everybody thinks. Then black holes just go around and as if like a vacuum cleaner takes things in, sucks things in. No, it doesn't. A black hole has an effect of drawing things in only in its immediate neighborhood. And so please don't go near it. You'll get drawn into a black hole. But if the sun today could turn into a black hole, I just told you it wouldn't. If it could turn into a black hole, nothing else will happen. We are not going to fall into the sun. It'll become very dark. But the planets won't fall in the sun, right? Because the sun's effect of pulling things in reaches just about Mercury, or not even there, right? So you cannot, nothing will fall in. So these are things that you should know. How do you find a black hole? That's a picture of a black hole. It's black. You see things from the light that comes from it, right? A black hole by definition doesn't emit anything. So how can you see a black hole? You can't. Okay. So when I was a student in Cambridge, for example, I took my first black hole course from the great man, Stephen Hawking himself. And at that time, Hawking had a bets with many famous people around the earth saying, black holes can never be found. I'm teaching black holes, but they can never be found because of the following reason. You can't detect them. Where is the light that's going to come from the black holes? However, we have a saying in Bengali which says that if you have rotting fish, you can't cover it with leaves. Right? You'll smell it. So the idea is you don't have to see a black hole, but you can feel it. And so I'll spend the rest of my talk here talking about how you can find these things. Hawking was proved wrong very, very fast and lost all his bets because people found ingenious ways of finding these black holes. And I'll talk about 3 different kinds of ways of finding black holes if I have time. And all of them are connected to India's scientific aspirations right now. Indians are very, very big connected in black hole research. There are 3 kinds of black holes that we know of. Actually 2 kinds. One are what we call stellar mass black holes. These are black holes that have formed from stars. Stars have collapsed. Stars can collapse at the end of their lives when stars are stars because they have a fusion engine in the middle. They are nuclear fusion. They are producing energy. When the fuel runs out, they can collapse. And if the stars are more than about 4 or 5 times the size of the sun, they will turn into black holes. Chandrasekhar showed that. Our sun won't. It will turn into something called a white dwarf. Now stars are a few times the mass of the sun. They can turn into black holes. Similarly, every galaxy in the universe has a supermassive black hole in the middle. There are many, in each galaxy, there are 100 billion stars, 10 to the power 11 stars, out of which there are millions of black holes, stellar mass black holes. Because stars, when they die, many of them turn into black holes. However, in the middle of each galaxy, our galaxy is called the Milky Way, it has 10 to the 11 stars, the sun is one of them, is one black hole which is supermassive. It is at least 1 million times to 1 billion times. 1 million is 10 lakhs, as you know. 1 million to 1 billion times the mass of of the sun. And these are called supermassive black holes. So for a long time, people have been saying, why 2 kinds? Why 10 times the mass of a star, of our sun, and 1 million times the mass of a sun? So why not 10,000 or 1,000 or 100? And there hasn't been any answer. Secondly, people would ask, how are these huge, massive black holes formed? I know stars can collapse to form the stellar mass black holes. If you merge these things to make bigger and bigger black holes, then why don't we see the things in between? Only now we've actually started to some things in between, and these are called mid-mass black holes. It's a controversial subject, but we've started to see things that are between the stellar mass and stuff, and I'll show you a few examples. So what's a galaxy? our galaxy looks like this, the Milky Way. So let's look at how to find these black holes. The first thing, how do I find the black hole that's in the middle of our galaxy? One of them, one black hole per galaxy. So here's our galaxy. We live in a galaxy. We call it the Milky Way, Akash Ganga in most Indian languages. And this looks like this. It's very interesting. If you look from the side, it's flat. It's like a chapati with a little bulge in the middle, more like a chapati, right? And the sun is not in the middle, it's somewhere offset from the middle, and the earth around the sun. So you can see when you look up in the sky and you see the stars are actually all the stars that are in this little band in there. So we see only those stars. But if you can look towards the middle of our galaxy, it's like a river. That's why we call it Akash Ganga. You see it much better from the southern hemisphere. But on a very dark night, if you're away from big cities, you can see it from India as well, many places. And many of you would have seen the Milky Way, right? So in the middle of that, and you can see, this is of course not a real picture. You can't take a real picture because you're inside it. This is an artist's impression. And right in the middle, you can see in the plane of our galaxy, there's a lot of dust. And this dust, which is black, which actually absorbs light, is left over from when the stars are formed. The stars forming process is not a very efficient process. It leaves behind a lot of material, which is like dust. So this is full of dust. And if you look at it from on top, it looks like that, and you can see that's the middle, where that's right in the middle is the black hole, which you won't be able to see. And the sun is going around the galaxy. It's gone around the whole galaxy 20 times in its lifetime, and it goes on. Okay. Now, what we want to do is to find this black hole that's in the middle of our galaxy. But you can't find a black hole, right? You can't see a black hole. So here's a picture. This is a real picture of where we believe the middle of our galaxy is, Sagittarius. And Sagittarius A star is where the black hole is. That's the position. Of course you can't see it because it's black. But there are stars around it. So if we can take those stars that are around it very near the black hole and find how fast they move, we can figure out that there's a black hole here. Just like you look at all the planets that are going around the sun, and even if you didn't see the sun, you can guess that there's a sun there, which is pulling all these planets around it. Right? So you'll have to look at these complex star orbits. There is a problem with that, and that is, if you are on the Earth, you see the light that comes from the stars, they come through the atmosphere. The atmosphere is many, 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 many layers. And the atmosphere is 100 kilometers high. And at each point in the atmosphere, the temperature, the pressure, the density varies. So the light is coming in a zigzag, zigzag, zigzag fashion. It is not coming straight to your eyes. Right? And so if you look, here's a star, you can see, and that star's image, let me see, a star's image will move on your camera very fast because it is coming through all this air to you. This is why stars twinkle. Your eye sees the star twinkle because the star's light is not coming in one. So now you take a long exposure of a star, it's going to be blurred completely. Because this is moving like that. Now if you want to pick out stars that are very close to the black hole at the center of our galaxy, you'll see a big blob because of the atmosphere. Now what humans have done is amazing. They figured out a way to beat the effect of the atmosphere, and this is called adaptive optics, and I'm going to try to explain that to you. Here's the biggest telescope in the world right now, called the Keck, which is on Hawaii. 2 telescopes. It's built, and there's an Indian connection, which I'll come to in a minute. That's the telescope, it's mirror. 10 meters in diameter, but it's not a single mirror. It's got 36 segments which are hexagonal. And we figured out that these 36 mirrors can be moved 1,000 times a second to change its shape. So adaptive optics is such that what you do is you have a little telescope observing a star, and it figures out how its image is moving. Like I showed you, it feeds that through a computer into this mirror, and the mirror changes its shape such that it actually receives the image of the star in the same place. Can you imagine that? And this has been done from the 1980s, 1990s. So this is what happens. Here's the galactic center, the Sagittarius A star. This is where Stephen Hawking said there's no way you can find it because you can't even image these stars. That's what it looks like. With adaptive optics in the Keck, that's what it looks like. You can see individual stars. This is real picture. And this was done from the 90s till the current time. And for this, a few years ago, these two people got the Nobel Prize for actually detecting the black hole in the middle of our galaxy by studying the motion of the stars around the center of our galaxy. Andrea Ghez and her group at UCLA used the Keck telescope. Reinhard Genzel in Munich used the telescopes in the southern hemisphere, which belong to Europe, called the Very Large Telescope. Astronomers are horrible at naming telescopes. It's called the Very Large Telescope. The next big one they're building is called the Extremely Large Telescope. And then one after that will be the Outrageously Large Telescope, or overwhelming, anyway. So this is the Very Large Telescope, and that's the Keck. Both of them started around 1993-94, and this is what they got. So you can see that this is, if you look at the top corner, you will see the year of observation. 20,004.7 means July of 2004. This is all done by adaptive optics. And you can see all these stars are actually real stars around the black hole, which is there, which you can't see with that asterisk mark. I'll play it again. And this is starting from 95 in Andrea Gez's case, all the way up to her Nobel Prize, which was in 2018. Look at this. And you can see these stars moving day by day by day, you observe, and you can have these nice closed orbits like planets going around the sun. S2 takes 15 years. In 15 years, she figured out where the black hole is and what its mass is. Right? Even long before the 15 years, we knew that the mass had been found. For those who are mathematically minded, it's called Kepler's laws. There's a relativistic version of Kepler's laws. And in from Kepler's third law, you can just plug it in, use some special relativity, and it turns out it's 4 times 10 to the 6, 4 million times the mass of the sun, right in the middle there. Right? And you can see that Sagittarius A star is sitting at, like Kepler's law says, at a focus of the ellipse. So that's one way you can find black holes. You don't have to see them, but you have to look at the orbits around them. You can't do this for many, you can do this only for our own galaxy, because for other galaxies to get that close, we don't have that technology yet. We will, and I'll tell you how we will. So that's a supermassive black hole in the middle of our galaxy. Let's see how we can deal with a stellar mass black hole in our galaxy. So this is something that I've worked on quite a bit. What will happen, as I said, the stars die, they produce these black holes. Imagine now, stars, here's another interesting fact. More than half the stars in our galaxy don't live alone. Like humans, they don't like living alone. They live in pairs. They're called binary stars. Our sun is an exception. Most planets should see 2 suns in the sky. In our solar system, Jupiter almost became a star. It didn't. If it were 10 times larger, it would have become a star. So normally there are 2 stars going around each other. Now one of them would be bigger than the other. Bigger stars evolve fast, they die faster. So one of those stars might turn into a black hole. So its outer parts explode, the inner parts collapse, like Chandrasekhar said, and they form. So that's the black hole, and it's now actually orbiting a normal star. Now the normal star soon will get to a phase where its fuel is getting exhausted, and it's going to get larger, becoming a red giant. As it becomes larger, the outer parts of that star will get weaker and weaker gravitational pull from the middle of the star. So that thing that's there nearby, the black hole, is going to start pulling things, right? So it's going to start pulling material from this companion star on itself. Now, these two are moving around each other. So actually things that are moving in circles cannot go directly in a straight line into the black hole. This is why our Earth never will fall into the sun, because it's always going, it's got angular momentum conservation. So that stuff that goes into that black hole is going to form a disk around that black hole. It's called an accretion disk. And it'll stay there for a long time before that material falls into that black hole. Now, because the black hole is such an extreme object, very dense, sitting there, the stuff that's orbiting the black hole will get very hot. It will become 1,000,000 degrees hot, 10 million degrees hot, right? The material that's fallen in. So now is how you find that. So what you do is you look for things that are 10 million degrees hot, gas. And at 10 million degrees, a gas does not emit light. Our sun is 6,000 degrees hot. It emits normal light that we see with our eyes. 10 million degrees hot gas emits X-rays. So you have to build an X-ray telescope. Oops. So here you are. It's an artist's impression of material falling onto a black hole. You can see that black hole in the middle, that little spot. I won't be able to detect it, but who cares? It's the thing around it that will emit X-rays, right? You can see light exists in all forms. It's the same thing, X-rays, ultraviolet, radio waves, normal light that we actually see with our eyes. They're all the same thing, it just depends, it differs in energy, how hot things are as they emit things. So these black hole accretion disks emit X-rays because they're very, very hot, much hotter than the sun. The problem is with our atmosphere again. Our atmosphere only lets in the kind of light that our eyes are sensitive to. Isn't that a coincidence? You can see this entire expanse, the atmosphere, it's around here where it lets in light. That's what our eyes see. And some radio. All the others, which are X-rays, gamma rays, ultraviolet, infrared, they're all stopped by the atmosphere. Rattlesnakes only can see infrared. There are no rattlesnake astronomers. They don't know there are stars out there. If our eyes could only see infrared or ultraviolet, imagine how much astronomy we would have done, right? So, but the black holes that we want to see are in the 10 nanometers, 1 nanometer, this region. I don't know why this is not working, but this region. So this is why we have to go to space, and this is why astrophysics is such a new subject. Most of astrophysics that we do now, you have to go to space to do it. We have to send telescopes into space, because we have to see all that entire source of light, other than the light that we've been traditionally seeing for thousands of years. And the Galileo's telescopes helped us see, right? So we have started building space-borne telescopes. This is India's telescope, X-ray telescope, that I was very happy to be part of. Dr. Kasturi Rangan started this in the 90s, and we launched this in 2015. It has an amazing array of 5 telescopes, and 2 of them are X-ray telescopes that they can actually they can detect X-rays from space, and it's above the atmosphere. I was involved, as you heard, in NASA's Chandra X-ray telescope. It's named after Chandrasekhar because he predicted black holes. Right? So NASA named the telescopes, launched in 1999, and I was very much involved in building one of its detectors at Harvard with a NASA grant. It is a very interesting observatory. It's a telescope that has a very long orbit. It has to take the telescope away from the surroundings of the Earth because there are magnetic fields around the Earth and radiation belts. So it goes very far away. It takes about 64 hours to go and come back. Right? Our Hubble Space Telescope or the space station or Astrosat takes 90 minutes. 64 hours. And out of the 64 hours, it is shut down for 35 hours because in the radiation belts, its sensitive instruments are going to get fried. There's also another very interesting thing that I wanted to point out to you, and this is another innovation that we've been doing in India. How do you build a mirror to make an image out of X-rays? How do you make a mirror to make an image out of light? You have a glass or aluminum surface, light comes and falls on it, gets reflected, and then you can make an image. You all know X-rays don't do that. X-rays go right through. That's how you get, go to a hospital and get an image out of inside your. So you can't be. Then how do you get an image out of an X-rays? Here's how you do it. Think of the following. You're hitting a football against a fence. The football is larger than the spacing between the fences, and that is why it comes back. That's why light comes back from normal materials. X-rays have very high energy, so its wavelength is very small. And that's why it goes through. It's smaller than the space between the atoms or molecules on surfaces. You can see that a ping pong ball, if you throw against the fence, it'll go right through. So somebody had this amazing idea that the way to solve this is to turn the fence. So then you throw a ping pong ball at a fence that's turned, it's going to hit, right? So X-ray telescopes are built like this. It is built such that light comes at very small angle to the surface. Not like that, but like that. And you slowly reflect X-rays over a very long surface to the instrument which captures it. And I saw this being built when I worked for Chandra at Harvard. The first wonderful, wonderful X-ray telescope that was built, mirrors that were built for Chandra, actually does that and produces image same quality as that of the Hubble Space Telescope in the optical, but in X-rays. And so you can also stack these. Because they're grazing incidence, you can have many mirrors which are concentric with each other. Chandra has 4, Astrosat has, that's the Astrosat mirror. This was built in the Tata Institute in Bombay by K.P. Singh and his group. Fantastic job of building a soft X-ray mirror. It has 45 mirrors in there, which are all concentric like that, right? Now, since I was part of the Chandra team, we had guaranteed time to observe for very long periods of time the sky. And we're doing still there. 1999, still working. Every year we get some time to observe something. As we have very deep images of certain favorite objects. And I'll show you one. Here's a galaxy called Centaurus A, which is a galaxy near us. It looks like this. This is a normal picture taken by a small telescope on Earth. Optical picture that our eyes will see. You can take a telescope and see this. So everything, because this is normal light, everything in this picture is a few thousand degrees hot. Right? Like our sun is 6,000 degrees hot. Okay? But there's a very powerful black hole in the middle of this galaxy, which is almost 1,000 times more massive than our black hole. How do you find it? You go to X-rays. So one of the targets we had at Chandra, and we've observed it for 25 years now, of the same galaxy in X-rays. What do we see? So everything in this picture is a few thousand degrees hot. Everything in this picture is a few million degrees hot. Right? 1,000 million. You can see that there is a very strong black hole in the middle, which is actually emitting a huge kind of jet of gas. It's vomiting out gas, very hot. But all of these things that you see are binary stars in which one of them is a neutron star or a black hole. I had a PhD student whose entire PhD thesis was on that picture, analyzing every point in there. And he found that most of those, he could find the mass of the black hole, which is causing the X-rays. Here you are, Hawking proved wrong again. You can find the black holes, not by observing the black hole, but its neighboring star, from which it is drawing matter and heating it up, right? So now, until very recently, most of the black holes we knew were found this way. This is the smallest black hole we know, found from its X-rays and gamma rays, about 5 times the mass of the sun. But it's about 8,000 light years away. Don't be afraid. The nearest one we know now is about 2,000 light years away. And so 2,000 light years. It's not coming to get you, okay? So I'm going to spend I know that I'm running out of time. I'm exactly at 40 minutes right now. And I'm going to take 10 more minutes, okay? To talk about the third connection, which is going to be very important. In India, we have these mega science projects, which cost a few thousand crores each. And over the last year, we've been essentially joining these mega projects all over the world, joining hands with other countries. For the first time, I mean, Indian scientists were not really collaborative with the rest of the world. But now with, experimental projects, we are getting there. The top 3 are the ones that we are doing in astronomy, and all of them are very relevant. I'll talk about the first 2. The 30-meter telescope, which is actually still in jeopardy, is supposed to be in Hawaii, which will become one of the largest telescopes in the world. It is a larger version of the Keck telescope I showed you. The Keck telescope had 36 mirrors, 10 meters across. This is going to be 30 meters across. It's going to have 492 mirrors. And 5 countries are building this, including India. India owns 10% of it. And India, of that 10%, 75% is in kind, which means India is building things. It's not just giving cash, right? So you can see Andrea Ghez, who found a black hole in the middle of our galaxy. She's from the US side. And I've been on the board for many, many times. I was in charge of, at one point, the TMT India project as director of IUCA. Andrea, her idea is to use this to do the same thing in other galaxies, because this is such a big telescope. It's going to. Of these telescopes, of these components, India is building the control system for all the 492 mirrors that are going to be moving. As I told you, they have to be moving in adaptive optics to make the image quality. Yeah? And we scoured India to find MSMEs and small industry who can build things like that at the international standard. We found unlikely little industry, family-owned in Pondicherry, in Jamshedpur, in Indore, who could build little parts of these things that are needed to actually change move these mirrors. Also, half of the mirrors are going to be polished in Bangalore by the Indian Institute of Astrophysics. So we are actually deep in the project. The only problem is that at Hawaii, we've run into a political issue where the native Hawaiians are trying to stop the telescope from being built. That's a separate issue. The last thing I'll talk about is gravitational waves, in which, of course, for India is a big, big thing. And I don't have much time to talk much about it, but I'll just highlight the Indian connection. When gravitational waves were discovered, gravitational waves are very interesting things, because I already told you that Einstein said that gravity is distortion of space-time. Well, if something moves in space, then it causes ripples, like a duck moving across a pond. It'll cause ripples. These ripples propagate as waves. So if things collide with each other in space, or they move, they will create ripples. And Einstein predicted it in 1916 and said, look, it's going to be very, very faint. Nobody will ever detect them. But this effect will be there. Now, when they were discovered exactly 100 years after Einstein predicted them, the interesting thing was the discovery paper had 1,000 authors, 40 of them from India, right? And it turns out the method they used to find that gravitational wave was actually the work of an Indian in 1970, Vishweshwara's famous Nature paper, which showed what will happen when two black holes collide. That was the third reference in the paper. So the first thing that was discovered 100 years after Einstein was the signature of the gravitational waves, which are ripples. The space itself is vibrating. When two black holes that are stellar mass black holes that are merging with each other. Now what happens when two black holes merge? These gravitational waves propagate through space, and they propagate in a way which is very interesting. But it propagates in a way where space oscillates in one direction and oscillates in a different way in the perpendicular direction. So when this is compressing, this is expanding, and things like that. So if you can think of that and find a way of detecting it, you can do it, except that, so I'll come back to that in a minute, except that the amount of change that can happen is of the order of 10 to the power minus 18 meters if your detector is a kilometer across. What is 10 to the power minus 18 meters? How many of you know this? That's a meter. Your hair is about 10,000 times smaller. If you take the wavelength of light, that's another 100 times smaller. You've gone only 1, 2, 3, 4, 5, 6. 10 to the power minus 6. Another 10,000 times smaller is an atom. That's only 10 to the minus 10. If you're going to a nucleus is within an atom, that's 10 to the minus 15, and I'm talking of something that's even 1,000 times smaller. This is why Einstein wrote a whole paper saying it's impossible. You can't detect this. But people have, right? And the way people have done that is build this amazing instrument called LIGO, which is in the US. Initially were two in the US, and now there's one in Europe and one in Japan, and there'll be one in India. So this is such that it has got over 4 kilometers laser beams bouncing off mirrors and coming out and being combined and staying in equilibrium. And if a gravitational wave passes through one of these, it will not pass through the other. And so one of them will oscillate and the other won't, and it'll go out of balance. That's the idea. It's very, very sensitive. It is so sensitive that when the first detection happened in America, one in Louisiana and one in Seattle, near Seattle, we waited for 6 months before we announced it to the rest of the world, because we have to figure out that we have eliminated everything else. There was a thunderstorm in Nairobi in Kenya at the same time, and we feared that we had detected that, right, from Seattle. These things detect every single wave that bashes both coasts of America. It's that sensitive. You have to be that sensitive to go down to those things, right? And we have to build one in India, as you can see soon. So the first one that was discovered was this one. I remember this very one. I just become director of IUCAA 2 weeks ago. Before this, we're not prepared for this. Suddenly this thing came. It was in the engineering run, and found the first, it was found from these two observatories across, as I said, in Washington State and in Louisiana. How massive were these black holes? They were about 30 times the mass of the sun. They collided and produced something that was 60 times the mass of the sun. I had one of my IUCAA students actually draw a picture of how big the Schwarzschild radius of that black hole would be. They're size of Indian states, right? One the size of Karnataka and one the size of, like, and to have something the size of half of Madhya Pradesh maybe. That's the kind of size you're talking about. So now we have a whole, but this is not the new picture. The new picture is very confusing. I showed a picture in which you can see that this is the number of times, the black holes that have been found by LIGO, number of times the mass of the sun. And you can see that before this, all of these yellow ones were the ones we were finding with Chandra and the X-ray telescopes. The LIGO discoveries have all been more massive, and we've gone all the way up to 185. I told you, what's missing is more than 100, because there are no stars that are more than 100 times the mass of the sun in our galaxy. So how do you produce something that is 185 times? So we found that there were two things, 190 and 180, they got together and produced something like that, yeah? So these black holes are colliding, producing more and more massive stars. This is only the beginning. We now have 175 detections. This doesn't show all of them. And things are increasing. As you can see, the detectors are two in America, one called Virgo, which is in Pisa, one called Kagra, which is in Japan, and we are going to build one in Hingoli district in Maharashtra, central Maharashtra. And only a few months ago, the Indian government actually finally sanctioned the money. I haven't seen the money yet, but it's about 2,600 crores to build it on Indian soil. The first time we'll build something of this. That's what the architects think it'll look like, in the middle of nowhere in Hingoli. You really have to build it somewhere which is so far away from human habitation. We have to find a place that is at least 30 kilometers from the nearest railway line. Find me a place in India that is away, 30 kilometers away from a railway line. We had some undergraduates write a little Python program to take the whole map of India, and they found 30 such places, and we went and put a earthquake measuring, or a seismometer there to find out how the ground itself vibrates, and we found this place. Right. So we have social media and everything. Please follow what's going to happen in LIGO India. India is going to be one of the major places where we are now going to discover black holes. I just wanted to put some books up which talk about black hole physics in general, but for your reference, thank you very much for listening to me, and I'm very happy to answer questions. Thank you very much.
One of the audience has any question for sir, they can ask. Kindly raise your hands so that I can reach you.
Yes, there's a question there. Any mics? Doubt. And this is why I talked about Newton and Einstein and the tradition that we have of physics that we study, which comes in a kind of unbroken arc from Newton, really. We don't have an unbroken arc of knowledge of this kind within the Indian tradition. We have fantastic insights given by certain schools. We have Aryabhatta talking about, we have Bhaskara, the second Bhaskara, Madhava, talking about various aspects of astronomy and physics. There are concepts of what sounds like gravitation from a lot of things that come from these traditions. But actually something that relates this idea of something becoming so small that the escape velocity will become larger than the speed of light needs what Newton formulated as gravity, which is that formula I showed you, which is mass over r squared. And that was not there in that form, in the mathematical form in the Indian tradition. Qualitatively, there was a lot there. And just like I showed you of the British text or the Laplace's text that showed that if you take a star and make it smaller, it might produce something like a black hole, qualitatively people might have thought about it, but you really needed that mathematical form. And that mathematical form, to prove that, Newton needed to invent calculus. Some form of calculus was already there by Madhava in the 13th century in Kerala. But for Madhava, that move to physics was not there. So I have not come across, and maybe we will, of this idea. But the idea of places in the universe from which nothing can emerge, maybe very qualitatively was there.
Okay. And a related question
Yes.
was like a lot of the Indian text, these people.
Almost 200
but
black
that's
holes
within
that we found, like-
within our experience.
So we don't have to invoke higher dimensions to understand LIGO black holes. What we might have to do is the following. People have a lot of ideas about what is inside a black hole. We don't know. We don't have the physics to find out what's inside that Schwarzschild radius. What happens to things that fall into a black hole? And a lot of people think that in order to know that, you need a quantum theory of gravity. We haven't merged quantum mechanics and general relativity together into understanding a quantum theory of gravity. And the theories of quantum gravity, which are by no means a universally adopted thing yet, it hasn't become one, might have to invoke higher dimensions. A lot of the formulation of quantum gravity is done to people who do string theory, people who do various other kinds of things, and they invoke higher dimensions, particularly in the early years of the universe. And that's a whole subject. But that's a very mathematical subject. We don't know even how they will manifest themselves into an experiment that we might perform to detect something. But that's a very, very interesting subject. Yeah,
Thank you.
There was a question.
Yes, sir. Black, you told me that since light is also not coming out, that's black. Why hole? It's not hole. Yeah, it's mass.
John Wheeler is responsible for it, and I don't know what he was thinking, but it's like a hole in space, isn't it? I mean, it's like the pictures we showed you. It's like space is there, and a kind of, I think, let me see if I can go back to that slide I had, which was there when I actually showed you Einstein's idea. Yeah, I don't think I can. So that's the reason, I think. Oops. You can see the idea is that space is distorted by the sun. But when it's a black hole, it is distorted so much, it becomes almost like nothing can come out. It's like light is trying to come out, it can't come out. So that looks like a hole, right? And so that's why I think it came. I mean, it's some of these, black, why? Because it's absence of light. But some of these names often lead to a lot of confusions. You hear dark matter and dark energy, and people think, oh my God, what is dark energy? It's just, it has a... Similarly, black holes. Somebody, Big Bang. What's a Big Bang? It wasn't a bang, it wasn't big. Right? So sometimes it is, the names don't mean much.
Visual signifies about.
Yeah, a little, yes, that's right, yes. Thanks, Sudhir.
Good evening,
What
sir.
I want to ask is probably some students may be interested too.
Yes. I would like to see if some of the students who've come here, would you like to ask some questions? Where are they?
Sir, good evening, sir.
Yes, I can see people at the back. You're backlit. Tell me.
Sir, I am Dishita Agarwal from MGT Girls School.
Wonderful.
My question is that if the sun dies, so the earth would stop revolving.
No, not at all. Why would... Now, sun dies meaning what? Sun can't die. By a stellar death, I mean it stops producing light. How does it produce light right now? It has a nuclear fusion reaction going on in its middle, and it fuses hydrogen nuclei into helium, and as a result, it produces energy. Right? That's what happens. Now, the amount of hydrogen in the sun is limited. It is a finite amount. We have reached about half the lifetime of the sun. It's been there for 4.5 billion years. It's going to last for about a little bit more than 9 billion years. So when the 9 billion years mark comes, it's not going to be in a lifetime of you and me, but when that comes, then what's going to happen is that all the hydrogen is going to go. Then the sun can't synthesize helium from it anymore, so its light is going to go out, and that's what it means by the sun death. But the mass of the sun is going to be there. It's just going to be dark. And because it has gravity, the earth is going to turn around the sun, right? Because the gravity is not going to change.
Okay.
The mass is the same. The light is just going to go.
Thank you, sir.
It's going to be very dark, of course. And I don't think you and I will be there. I don't think humans will be there by then. But of course, if sun's light is not there, life on Earth is doomed. I'm just pretty certain there won't be any life by then. No, it will become what is known as a white dwarf. So there are 3 different kinds of things. I didn't talk about it today, which Chandrasekhar predicted. So things that are kind of the mass of the sun, till about 1.5 times the mass of the sun, they will all turn into what is known as white dwarfs. White dwarfs are kind of the size of the Earth. The whole star will shrink to something that the size of the Earth, a planet. And it's going to be there, not emitting anything. So there are many white dwarfs around. We know many white dwarfs around. Now, if it is even more massive, so between about, say, 1.5 times the mass of the sun and maybe 4 times the mass of the sun, then Chandrasekhar showed that it's going to start collapsing again. And due to quantum mechanical effects, it's going to be stopped. It will become a neutron star. It's going to be made entirely in neutrons. It's 10 kilometers across, size of Jaipur, but the whole mass of the sun, right? And there are many neutron stars around. We've detected a lot. They're called pulsars. And then Chandrasekhar showed if it's more than 4, then even neutrons can't stop it. It's going to further collapse and go into what is known as a black hole. Yeah. So the sun is not good because by definition the sun is only one solar mass. Anybody? Yes. If anybody up there amongst the students think of more questions, tell me. Yes. Let's go there. Let's get a mic there. Question.
You have talked about the star
A very good question. What happens after a black hole is formed? Now,
is it the end in itself?
no, this is interesting. This is very interesting. So this is something that in the 60s, 70s, Stephen Hawking became very famous for asking this question. And Stephen Hawking came up with a very interesting idea, which is so interesting that he published it in a popular magazine, Scientific American, before he published it into journals. It's called Hawking radiation. And what he said was, and you have to be a little technical to understand this, but what happens in a quantum universe is that in space, always energy packets or light packets are always breaking up into particles and antiparticles and then recombining into energy. Mass and energy are interchangeable, E equals mc squared. So this is happening all the time in the quantum world. Hawking said, think you are near the event horizon or Schwarzschild radius of a black hole. And suddenly, from energy, 2 particles form. One particle and one antiparticle. And one falls into the black hole. What happens? The other one doesn't. So you have created a particle, right? And where does that particle go? That particle will take out some energy from the black hole. The black hole's energy, net energy, is going to decrease because a negative particle has fallen into it. So Hawking said, by this process, a black hole will actually slowly emit energy and thus diminish in size and die. Now then you can work out how long it takes. A black hole that is the same mass as our sun will take 10 to the power 60 years to die. We're only 10 to the power 10 years old. Very, very long time. So black holes will never completely die. But there is a chance of a black hole diminishing in size. It's a quantum effect. Huh?
It can't exceed the speed of...
No. I mean, it will remain a black hole. It's just becoming a... So, just like things can fall into a black hole and its energy can go up, its mass can go up. This is a mechanism of its going down. So you can destroy a black hole very slowly.
It's a theoretically, we can say.
No, theoretical. I mean, if I talked about the mass of a normal stellar mass black hole.
Right.
If it's a very massive black hole, its Hawking radiation is more. Right?
There's no experimental evidence.
No, not yet. No. There's no way. We don't have anywhere near.
But that's very interesting. We are having a universe where we have got number of black holes.
Many.
And they are
What I mean, number meaning millions.
Like that.
Our galaxy has millions of them.
And what they
and there are billions of galaxies.
Yeah, they can they are going to impact the stars nearby. You know, they can all.
In fact, one of the things,
get into radiation.
it was in science fiction, but now people are realistically thinking of it. People are thinking in the future of actually extracting energy, actually usable energy out of black holes.
Oh, it's very interesting. Thank
Very
you.
interesting
There are so
stuff.
many people, ma'am. We are running out of time. There is a student standing for so long.
Okay,
Please
another one.
Take a question.
Good evening, sir.
Evening.
I am Punjika from MGT Girls School, and I wanted to ask, is it possible for a black hole to shrink or disappear?
Yes, that's exactly what I talked about. So a black hole can shrink by emitting mass using what is known as Hawking radiation, but it's a very, very slow process. And it's a quantum mechanical phenomenon. Classically, you can't do it, but this is the only way we know so far. Now, you know, this subject is very new. When I was a student like you, these things were being worked out. Right? Hawking published this paper of this kind of stuff when I was in school. So you can see things are actually being done now. So by the time you become an astronomer, or maybe you will do it, this will be, we'll know much more about it. So this is a very exciting time to work on these things, to be alive and also to be an astronomer. Yes?
The constitution of a black hole made up of
I don't know. This is a very good question, and the answer is we don't know.
Okay.
And that is because as matter crosses the event horizon of a black hole, there is no way we can get any information about it from inside. And the physics that we know, the way we know it breaks down. So we don't know. And again, it's up to those young people sitting at the back to develop first a theory of gravity that has quantized, and then we try to understand what could be inside, right?
Now we are running out of time. Sorry to interrupt, sir.
Sir,
Okay, let's Sudhir know.
Sir, actually you can discuss later on outside, please.
Let's give Sudhir one. Yeah, one.
Only interest the students. Students understand Kepler's law.
Yes. Can you give Professor Raniwala one? Yeah. He knows much more about black holes than I do, but
Students understand Kepler's law. Can you derive Kepler's law from Einstein's general theory of relativity? I haven't seen one derivative.
That's right. Special theory.
So if I can't derive it from general theory of relativity, and they know Kepler's law work very well, why should anybody believe in general theory of relativity? And hence, why should one believe in black holes, which can only be identified by their effect on other things, which I just say is my ignorance. So this is for students.
Sir, actually we are running out of time. The session is over.
This, but
and really sorry to interrupt. And you can discuss because it's a long question, it's a lengthy question. Sir can explain you later on. And now we have come to the close to this wonderful evening. And I thank sir a lot for this. And I extend my heartfelt gratitude to everyone who made today's Jigyasa talk such a memorable success. Our deepest thanks to Dr. Somak Roychoudhary for his enlightening and thought-provoking talk, and which has taken us to the fascinating journey of the mysterious universe and cosmos beyond. A special word of appreciation to Shri Umesh Mohan Sahayji and Shri N.C. Goyalji for his gracious presence and support, which added great warmth and dignity to this occasion. And finally, grateful thanks to the team RIC and team Jigyasa. Thank you very much to all the audience for being so curious and for being so patient. Thank you very much. Thank you, sir. Sorry to interrupt.